we are going to look at the end of chapter 9, which is on population training. And this technique will be a little different. It'll actually be related to stuff I brought up in the past, which is ways of reducing the multi-agent problem to a single agent learning problem by fixing the policies of other agents. And there are some advantages to training this way. One is that like we have a really well-defined objective when we do MDP learning, and we don't have to worry about equilibrium training and problems that occur with a multi-agent problem. But we're going to sort of have to deal with that in its own separate metagame problem that we'll see come up. Yeah, interestingly enough, some of the techniques that are brought up here are things that might sort of like naturally occur to you when you're looking at the multi-agent problem. And I have actually constructed some of these population training ideas, including in the most recent stuff we did, looking at sort of AlphaZero type of training pipeline, where you might have like generations of agents and you want to judge whether the agents are making progress in something like a two-player game. And that can be a difficult thing to judge in general, because like one agent could get better and the other agent's performance could get worse, or both agents could sort of have matching performance throughout the training process. And it's not like you can just look at the performance of one agent or like a single value and say, okay, this is making progress. So instead you have to rely on what we're going to see here, which is more looking at metagame values and matchups of different agents over time. So the goal of this type of population training is to have like a very general purpose multi-agent reinforcement learning algorithm. And we'll see that it can achieve that, although sometimes, like in the worst case scenario, to actually reach the type of solution we want, which might be like an equilibrium solution, that in the worst case scenario could require us to enumerate through like all of the different possible policies that a collection of agents could have in an environment. And that will be very, like that will not be feasible in general. So we're going to kind of hope that we end up sort of stumbling upon the correct solution before that happens. So let me just show a little bit of how this part of the chapter is outlined. So the idea behind a population training is actually very simple. The idea is like we have some environment, and it could be just any arbitrary environment with n agents. Well, look, it's easier to visualize when we just have two agents to work with, but we need to create an initial population of those agents. And that will usually be like the easiest thing we can do is just initialize a random policy, right? Because that's something we can always just trivially make. We just have a way of looking up which actions are available to the agent in any state. And we can always just freely create a policy where they just choose uniformly, randomly between those actions. Now, once we've created, if we just have one, initial, like we're going to call them like these generations of populations. So let's say at the beginning, we've just initialized a random policy for each agent. Now, at first, what we can do is just evaluate, what happens when all of those agents match up against each other. So in the case of a two-player environment, this will just be, for that pair. But in n or more, two or more agents, then these matchups will be, combinations of agents. So, but, if there's just one generation of each, it'll just be, we'll just say what happens when all these agents interact with, generation 1, for example. And that will produce a value or a reward value for each of those agents. Now, if it's a general sum game or a zero-sum game, we only need to keep track of one value. Sorry. Did I say general sum? I mean, if it's a common reward game or a zero-sum game, we only need to keep track of one value. But if it's a general sum game, then each agent can have a distinct reward, and we would need to track have like a value that summarizes how well did that particular agent do in this matchup. So we're done with the evaluation. In a general, sum situation, we'll have n different values, one for each. And then if we have multiple generations, then we're going to have more of these matchups to evaluate. In a two-player game, we'd have to evaluate all of the pairs of the generations that we've seen over time. And you can see this in this diagram, this metagame diagram. So this would be an example of, like, I haven't explained yet how we're actually, training these generations, but this corner, this upper corner of the diagram would represent the situation where we just initialize, let's say, a random policy for each agent. So this is like generation 1 of agent 1 and agent 2. And when they play in a general sum game, they'll be, this is the reward value for each distinct agent. And then as we keep adding generations, eventually we're going to build this larger metagame table. And the nice thing about this metagame is this connects directly back to what we looked at in the very early chapters of the book, where this is like a non-repeated game in the sense of game theory, like where we looked at games that can be represented with a matrix like this, where the goal is to figure out, if both agents are matching against each other and they're aware that they're going to have this matchup and that these are the possible outcomes, then what decision will they make? And the decision doesn't necessarily have to be a deterministic one. In these general games, sometimes the best decision an agent can make is a stochastic one, meaning that whenever the agents interact, it's not like they don't just pick one of these actions or things or policies in this case, but they might pick over a distribution of them. And that we'll get to when we talk about actually solving the metagame. But, if we go back to, so this is one of the notebooks I had from one of the really early, like maybe chapter 2 or 3 of the book, where we looked at these two-player games. And in this context, we were just looking at the games themselves. It's like, this is all there is to the world. We're just given these values. Like in this case, this is like a two-player general sum game. And in these situations, like if it's a zero-sum game, we were looking for these equilibrium solutions. And there was a lot of algebra we developed to solve these, but like here, we had gone through this example of, if you just simplify it to having 2 actions and 2 agents in the zero-sum game, then you can write down exactly, how to calculate this solution. And the solutions for these games, these are called normal form games, were all different types of equilibrium solutions. So in the case of a zero-sum game, we had the minimax solution, how to calculate it. And in the general sum case, we had these Nash equilibrium solutions. But, so the minimax solution is also a Nash equilibrium as well. It's just in the special case of having a zero-sum game. But these equilibrium solutions are what makes them an equilibrium solution is that all of the agents are stuck, in the sense that if they try to modify their behavior in any way, it will result in a worse outcome for them. So you can always verify you're in an equilibrium solution by just having the agents test if they change their behavior. What result does that have? And if they sort of try to probe all the different, ways that they could change their behavior, or you could think of it in terms of gradients in calculus, of like any sort of incremental modification to their policy will not result in any kind of improvement. So in minimax games, or in zero-sum games, there's a unique equilibrium solution. In general sum games, unfortunately, with the Nash equilibrium, there are lots of different equilibrium solutions, or it's not guaranteed to just be one. There could be many, and that means that if we're looking for an equilibrium, we could end up in any one of those, which can be a problem, if we can't actually distinguish those. So the other nice thing about the minimax solution, which is the first example we're going to look at we're going to look at an example that probably everyone's familiar with of like a rock paper scissors game where you have each agent has 3 actions available, and one player winning is always, you have draws where both players get 0 reward, but you also have, if a player wins, the other player necessarily loses. So that's what makes it a zero-sum game, is we can always sort of know the outcome for one player from the first player. So a win for one is always results in a loss for the other. And we found that we can come up with a more general way to calculate this minimax solution for any arbitrary normal form game. This is, one, which is why it's studied more. This is one of the equilibrium solutions that there actually is a reliable way to calculate it. We saw this is stuff we had gone over before, but there's a way to construct a linear program. It's just an optimization program, but this program will work for arbitrarily large minimax games. Of course, this is formulated where I believe it's they're generally only n equals 2. I mean, usually for a proper like zero-sum game, we're always thinking about 2 players, at least, and that's how these solutions are written. I guess in theory, you could have more players in a zero-sum game where the reward always sums to 0, but you're not going to have every pair summing to 0. So usually when we talk about zero-sum games, we're just talking about the 2-player situation. So this is showing a general sum game of this. But okay, let's talk about now like what it means when we create a new generation of policies. So here, go back to this. Or actually, we can just look at this pseudocode now. So this algorithm is going to construct the metagame, like I mentioned, by looking at, what happens when, with all the different combinations of policies that the agents can choose from. So what I was just showing were like normal form games. We have a game, like rock, paper, scissors is a game where you have like 3 actions for each player, and then you can make this grid of outcomes. Now, in this case of the metagame, these actions, where in a normal form game, each one of these columns would represent like a single action in the game. But now, each one of these columns is actually representing a policy that an agent would use to interact in whatever the game environment is, right? Which could be an environment with a lot of states. It's not necessarily, these normal form games there's just this single matrix, right? We want to look at more complex games, games with multiple states that can be transitioned into, think a game like chess or like tic-tac-toe, where, there's one of these matrix outcomes in any given state, but the state will evolve over time as players make moves in the game. So we can think of each one of these in the metagame as like, what does it mean for this action to be taken? Well, that means that for that episode of interaction, this agent is going to select actions according to this policy or this policy, right? Or like whichever policy it happens to pick. And then that, will have some expected outcome, which is represented here. Like, so this is like, what outcome can each player expect when player 2 selects from this policy and player 1 selects from this policy? Now, once we have formed the metagame, we can calculate, we can solve it. And by solving it, if it's a zero-sum game, that would mean finding the minimax solution. If it's a general sum game like this, it means coming up with some equilibrium solution that matches the criteria that we want. So it could just be finding one of the Nash equilibria in the game, or, it could mean something else. But whatever, solution we have, it should be something where, it makes sense that each player would make decisions according to that solution. So like, it's sort of, some of it is philosophical. It depends on like, how do you think the population of agents should behave? The nice thing about the solution being an equilibrium solution is that all the players are sort of locked into that behavior. But you could, use other criteria to solve it. Like what we talked about, other types of game solutions like correlated equilibrium solutions or Pareto optimal solutions. But you could basically apply any solution technique that we had for these normal form games that we started with, like to the metagame, right? Because the metagame is just one of these normal form games. So now, once we have a solution, the solution creates a policy, a distribution across these policies for each of the agents. So like this is being shown sort of abstractly here, but this means that the solution to this metagame is one in which this agent will select from the policies that have a bar here, right? And like this policy is more likely to be selected, and then these are less likely. And then here, like this is the most likely. So the metagame solution, it could look like this. It could also be a solution where there's just a single policy that is the best one. And we'll see that with a more concrete example. But whatever the case is, now we have for each agent a selection of policies that they should pick from within the metagame. Now, what we can do is, once we have these distributions, right, where we're calling, these are like the distributions that the agent is going to pick from in the metagame. Now, you could imagine, so we have this, we can say, okay, let's say for agent 2, let's just create an environment where agent 2 behaves according to this distribution. So like, if we start a new episode of the game, there's some chance it will be following this policy, and there's a smaller chance it will be following this or this policy. Now, once we have our like stochastic game, which is the full environment that we're trying to solve. Now, if you take a stochastic game like that and you fix the behavior of one of the other agents, like if it's a two agent game, then like you can imagine like a game like chess, right? If we fix the behavior of our opponent, now we've converted the game into a traditional Markov decision process that we can train a reinforcement learning algorithm on. And similarly, we can fix the behavior of the other agent and then think about training its opponent against that. So that's what's being listed here in this step of this algorithm. And the reason why it's a best response policy is that now, and we can always do this, is because once we create an MDP environment, then we know that there is an optimal policy in that environment that we can solve for. And there's some exact solution techniques if we're dealing with stochastic games and games with a lot of states. We may not be able to actually find the exact best response policy, but we can train an algorithm that gets progressively better performance. We can see when it converges, just like we would do in any ordinary reinforcement learning setting. So if we have two agents, then we need to train each agent against the current metagame solution of the other agent in the environment. And that is going to be equivalent to both agents learning a best response policy, right? And it's called the best response policy because it is a response to this current metagame solution, right? So what the current metagame solution says is like, let's say these are the available policies for every agent. It means that, okay, if these are the only policies that the agents can choose from, then the best they can do in the environment is to pick according to this metagame solution. Okay. Then after that, we're going to now go back to agent one and say, okay, at this current moment, this is agent two's optimal behavior in the environment. Now you can now try to exploit that and train a best response to that and see. Now, once that training is completed, we will then have a new policy to add, right? This prime policy that we then add to the metagame. Then we have to expand the metagame by evaluating this policy, right? So now we've trained the new policy against whatever this metagame solution was. Now we have to go, and there's these question marks are performance values that we are not aware of, right? Because we've never tested this matchup before, right? So now we have to test all of the new, the untested matchups. This will be all of the pairs that include only the new policy that we're training. And then once these question marks are filled in, we will then have a new metagame that we can produce a solution to. And that's what this process here, use single agent RL to train pi. In the book, this pi with the I minus, this means that these are some fixed policies for the other agents, right? Now, it's a little interesting the way we have to do this. When we create whatever this MDP environment we're creating, or we're training against, it's not that we want, it ends up being equivalent, I believe, but what we actually want is for each episode, so like we want in a given episode the opponent's behavior to be fixed so that they're selected according to this distribution. But once we've selected it, we fix it for the duration of that episode. And then when a new episode starts, we can then, potentially select a new policy according to the same distribution. But yeah, once we grow the population, then this loop just continues where we keep adding things to the metagame. Now, eventually, we'll reach a point where the metagame solution, hopefully this is what will happen, is not changing. So there'll be some selection of policies that are the metagame solution. And let's say once we've added a bunch of rows and columns to this metagame, we don't see this distribution is selecting things from earlier generations, right? So like we're adding later generations in later rows and columns. That would mean that the new best response policies that we're training are not being used. They're not yielding anything. Like we're not getting any better performance than we already had in the metagame. And that would be an indication that we have, that the process has converged and that we've actually found whatever like the true equilibrium solution is that we want for this game. Now, there is an example we can sort of walk through here, which is this rock, paper, scissors example. And I can also show what this looks like. If you're sort of like mocking this up or prototyping this, this is the first thing I looked at here. So like the first thing, like we need a way of evaluating the policies against each other. This is like this rollout function in the game. It takes this like some set of policies, right? So this will be like there's n of these, one for each agent, and it will just evaluate the outcome for each agent according to if the game is played where they're all using that policy. And then, yeah, there's some other, this is not that important here, some of this other stuff. But the main thing we have to do to implement this algorithm is to form the MDP that we're training against, right? So the idea is like, this is left over from like, I sort of built this multi-agent reinforcement learning on top of what the existing reinforcement learning package that I had. So What this function is, it's a way of converting a stochastic game, which is the original game that we're talking about, into an MDP under the constraint that we fix the policy of the other agents, right? And there's a version of it here where I just have a single policy for the other agent. And then there's another version of it here where we have to deal with these population distributions. So this is saying now for each other agent, there is some vector of policies that each other agent has, and there's a corresponding distribution of what this is like from the metagame solution of how those agents are going to select this policy on every episode. Now, I was trying to figure out a way of having this where I didn't have to keep like resetting the MDP every time, and I could create just a single environment. Like ideally, the way it's shown here in the pseudocode is that, we sort of use this single agent RL thing in between on each of these episodes, but there's sort of effectively like a new MDP here every time we go to a new episode because we have to resample the behavior of the other agents. But, if we have a learning algorithm that we want to go for like a lot of iterations and keep updating the policy instead of like here, this may not be the most convenient way to run whatever code we have, because then we have to sort of pass in the previously trained agent, and maybe we just want to run a long training process that will go over many different episodes without having to reset the MDP every time. So I was thinking of ways of doing that without disrupting too much, and I came up with, there's a pretty simple solution here, which is that we have the stochastic game, right? And there's a state, like there's something like each game has a state type, which is the container of information that what that state is. Like it could be like the game board or, the landscape, whatever the environment is representing. Now you can see here that for the MDP I'm constructing, we have to make a new step function. And this is the function that updates the environment state. And here it's a step function where it will update the environment state based on the action of our agent in the environment, right? And then we have to make sure that as part of that update, the other agents make their action selections automatically according to whatever these different policy distributions are. So we have this is passed into this function. So there's a way of doing this, which is that I can just augment the state. So here I've taken what is normally the state type, and I've said, okay, for the MDP we're making, we're gonna have the state where there's now two pieces to it. There's the state of the game that we're in, and then there's this vector that corresponds to what is the current generation of response policies from the other agents that they are using. And this will be just a vector of integers that will pull from whatever the available policies for the other agents are. Now, that means that this, whenever we do the step update, right, when we return here, this is returning the new state, it's going to get the new state, right? This line here is actually advancing the game state according to the stochastic game that is the underlying game that we have, right? And we're constructing this joint action using the policies of the other agents, right? And then we keep this generation vector the same, which means that while we're stepping through an episode, the actual policy that the other agents are using is fixed. So the place that the metagame solution comes in, these population distributions, comes in on the initialize. So there's, as part of this MDP we're making, there's a state initialization function. And this is the function where whenever we want like a fresh state or whenever we want to begin an episode, this is called and it produces an initial state. And as part of that initial state production, it samples from the population distribution, right? It samples it once and then it stays fixed until initialize state is called again, right? But this will only happen when an episode terminates. And that's exactly what is shown in this pseudocode here, is that we resample the policies of the other agents at the start of a new episode. So that is effectively what is happening here. And then you just have to make sure that whatever functions we have now, they have to accommodate this additional generation information, right? But this isn't actually relevant to the decision-making of our agent. This isn't like something the agent has access to. It's just a convenience thing for the step function so that it knows how to produce the action from the other agents. Yeah. So this is if we're doing this full-blown, procedure, we do need access to this. But if you are mocking this up, let's see. Oh yeah, okay. So for this initial test, you can see here when we're trying to set this up for the full problem, we have this general game and then use single agent RL. In general, we have to run like a full-blown, MDP training algorithm to get this best response policy. Now, we can sort of test the concept of this with a much simpler problem where getting the best response policy is not this involved. We don't have to do this full training thing. And that is what is shown here in this table with this rock, paper, scissors example. The idea is now we have this rock, paper, scissors game. We want to apply this policy response oracle concept to it. Okay? And the way this is set up, what's being shown here is the current list of generations here on every step of this algorithm. So on the first step, this is just a decision by the authors of the book, but they've chose to instantiate this where player 1 is selecting the action rock and player 2 is selecting paper. Now, for the first step, the metagame solution is always the same. It's trivial. It's just both agents have to choose the only available policy. And then these primes are always going to be in this table, the best response policy, right? And this is something we can just, get from just inspecting the problem. But we can see that if player 2 is playing paper, the best response for player 1 is to play scissors. And similarly, if player 1 is playing rock, then the best response for player 2 is paper. Okay, so we have now trained the best response policy, and now we're going to add these new policies to the list. Now, because in this case, the policies, we can just label a policy by the single action that's taken. So it's very easy to identify if a policy is already in the list or not. And that's why here there is not an additional policy added for player 2 because its best response was already in its list, right? We could, put a second P here. And in general, when we're doing this with a more complicated problem, once we train a policy, even if it is like functionally equivalent to an existing policy, it may be very hard to verify that. Like, let's say this policy list, these are just general functions that we have. Like we could just have, functions. It could be also left over from things other people gave us. Then, there's no way to just tell if two functions are equivalent in their behavior. I mean, you can tell if they're literally the same definition, but you can't tell if they're the same for what in their output behavior, unless you like test everything exhaustively, but there's no point in doing that. But in this case, we can just sort of combine the two P's together and just have one. And now we have a new metagame. Now here in the book, they haven't actually like shown, like drawn out the metagame and what it looks like. All they're showing here are the equilibrium solutions, which are not, completely straightforward. So we could probably we could just inspect it visually and see that this line makes sense. So both of these columns should represent the metagame solution to this. So in the case of agent 2, there's still only one available policy to choose from. So that is what it's, it's just going to, it's going to be 1 regardless. Now, for player 1, now there are 2 policies to choose from. We have to see in this metagame where player 1 can choose rock or scissors, and player 2 only has paper available. It is obvious that this is the best, like this is just the single best solution. There's no need to sample anything else because scissors will win every time against this, right? So we can see now. So now when we go on to train the best response on the next step, the response that we're going to have is that player 2 is going to be facing a player 1 that is exclusively choosing scissors. And then player 1 is going to be facing a player 2 that's exclusively choosing paper. Now, as we go on, we can see now the metagame solutions get more complicated. And this is where you actually have to compute the minimax solution for these game tables. And like we had that algorithm, that linear programming algorithm that can do that. For a game this simple, you can actually calculate it by hand. But we're not, that's only relevant for like really simple cases. And I think that to see this play out more, more thoroughly, we can look at this test function I made and see exactly what it's doing. So this is a test that's really only, this is like hard coded. It's really only suitable for this type of rock, paper, scissors game where we're actually applying this algorithm to what is already a normal form game, right? It's not like this general stochastic game with a lot of states, because in rock, paper, scissors or any of these games, right, we just have one effective play state, right? Like we have the play state where each player has to select one of the 3 actions. And that is then the only possible policies that exist for our list are going to be that list of actions, basically. So here, the way this is hard coded for 2 players in this game. So here I've created where these P1 init and P2 init correspond to this here. Here I'm labeling it with an integer, so this game happens to have like rock, paper, scissors. The actions are numbered in that order. Okay, so as a default setting for this or any normal form game I would apply this to, the most straightforward thing is just for each agent to start selecting action 1. But in the book for other, it's mostly because it ends up making this process take longer. They've done it this way. So now when we update the metagame using the first generation, so notice like I create this first generation, and the first generation is just the policy that returns P1 init and P2 init. So this is going to make a very simple metagame at first, and then we're going to solve it, which is just going to effectively create that distribution where each player selects one of the actions. Now, what happens in this loop is that I continue while there's progress. Then this is what I consider progress. So progress is that if we look at the last solution, and here the last solution is actually the metagame solution. So this is after we've updated, we've added all the new policies, the new best response policies. We have this metagame solution. And this is tracking whether the metagame is making progress. So if the equilibrium solution for each player is not changing, and here I'm not forcing them to be exactly the same, I'm just measuring these are both, going to be probability vectors. These are vectors over the generations that we've seen so far. And this is just measuring this distance between the vectors. So if they're close enough to 0, where if we compare all the probabilities, there's not a measurable difference between them, then I consider, like the metagame to be stagnant. in which case we've reached the equilibrium solution. Now, what happens when we train the new generation is, well, first of all, we have the population distributions. This is this metagame solution, when I call it, it produces those probability vectors in here for player 1 and player 2. Then this forms the MDP, right? So I take the game, the agent that I'm going to be training, like agent 1, and then I create the policy, I pass in the policies for the other agents, right? Other agent ins, or like these are the indices of the agents that is not the current agent I'm training the best response for. Then once I have the MDP, I can calculate the performance. Now in this case, instead of running a full-blown reinforcement learning algorithm on this, all I have to do is check the average performance. This is going to average the MDP when our agent selects all of the actions, right? So what this has done is it's saying, test all of the actions you have available, which in this case is just 1, 2, or 3, corresponding to rock, paper, or scissors. And then figure out which agent has the maximum performance, right? Like this is literally like, this is, you can't do this in most reinforcement learning problems because you can't exhaustively check the entire policy space because it is practically infinite. We have multiple states in the game. Here, the policy space is extremely small. It's just 3. So I can actually get the exact best response policy exactly like this. And you might say, well, it's possible that there are 2 different policies that are equally good. It's fine. It doesn't matter. We can actually just pick one of them and it doesn't change the algorithm at all, right? We're free to just pick any one of the best response, equally good best response policies. And that's actually, that is a well-known result from reinforcement learning, is that right, if we have a finite problem, right, like a finite MDP, then there always exists a deterministic policy that is optimal. Now, there's not just one, like in this case, it could be that like rock and paper are equally optimal, but they're each considered the optimal solution. Okay, so the nice thing is, even if we have something that deterministically gets policy, we're not losing out on anything, because the space of deterministic policies already includes the optimal policy. So this just very simply checks all of the actions available. Then it finds the one that works the best. And then it adds that to the history that we're keeping track of these generations, right? Where here we update the metagame with the new generation. And so we're forming the new generation with the index here that is the maximum performing action selection. And then we accumulate the metagame, and then over time we check if it's become stagnant or not, at which point we terminate. So now we can see how this actually runs on this rock, paper, scissors example. Let's look at what I actually return from this. So first of all, we have these messages that we have. Now, these messages here should correspond to the messages that we see actually in the textbook here. Although here I'm just listing what the best response policy is. So here, agents, yeah, so okay. So if we look at both, we should see how they correspond. So we have agent 1's best response is scissors, and agent 2's is paper. So that's here, scissors, and then paper. Then on the next generation, we have scissors and rock, right, which we see here. Then we have paper and paper. Now here in the book, it is true that at this point, rock is equivalently good to paper. Like I said, I'm only returning, I'm returning a deterministic best response. So either one of these is fine. Paper, paper, then we have paper, paper, scissors. Yeah, so then because I chose one of these, there's a slight deviation. Yeah, so this is going to deviate a little bit at this point because I didn't add both of these on this step. Yeah, but I do have a visualization of what this looks like over time. So we can track this. Now, we already know, we know that for the rock, paper, scissors game, we already know the metagame solution, or like the actual, like the full game solution. And it should be that the metagame value should end up being 0, which means that, you know, every game on average should end in a draw if both players play optimally. Optimal play, in this case, which is also shown in the book, is the uniformly random policy for each player. Now, this is where there's this distinction here where even though it looks like we're not really doing anything because like the metagame is sort of the same as the original game, there is a slight difference. And the difference is that the metagame is a game that can be repeated, right? So we're saying, like, let's say we're going to play some, you know, like recurring episodes of this, which in this case would be like multiple rounds of rock, paper, scissors. Well, if we look at like any single best response solution, it's just going to be this single deterministic action. Now, it turns out the minimax solution of rock, paper, scissors is this stochastic policy where we pick every one. But I said that when we're training these responses with conventional reinforcement learning, we are going to end up with a deterministic policy, which is a best response. And any one of these is not a correct, you know, optimal policy, but that's why we have the metagame solution. And in this case, the metagame solution is actually equivalent to if we were to just solve rock, paper, scissors with a minimax solver. And in this case, we did have to enumerate, right, all of the actions. So here we sort of built up the metagame. By the end of it, we're evaluating the metagame where there's 3 generations of policies, rock, paper, and scissors, right? So we've essentially just reconstructed the original like game that we could have solved. So it would be more efficient in this case to just solve this game like with all of the actions from the start. It's small enough that we can do that. But conceptually, we keep adding policies. Now, if you imagine, if instead of just single actions here, right, these were actually policies in a bigger environment, like a game of chess or something, you know, where now each one of these generations is a deterministic policy, sure, for chess, but now we can't just summarize it by saying a single action, right? It's going to be a separate optimal action selection in every state, right? And there's no way we could enumerate all of the different policies that exist in chess. We can't even enumerate all of the states that exist in chess. But if we were to go through this process and reach a point where the metagame got stagnant, where it reached an equilibrium, at some point, it's possible that that would happen long before we had to enumerate all of the different policies. And that's the only way this algorithm would actually be successful, is that there are large parts of the policy space that are just not relevant because they're so far away from optimal. We never have to consider them. We don't have to enumerate all of them. Right? So this is an example where we did have to enumerate everything, but we hope, and I'll show there's sort of a failure. So if this algorithm fails, the way it would most likely fail is that it would just run way too long and it would keep just adding new generations, but there's not any convergence of the metagame solution. Now, also, it's important to note the metagame value right here, because this is a zero-sum game, we're writing the value of player 1. In a general sum game, we would have a different metagame value for both players, or however, n players, each would have its own metagame value. So here we can see how the metagame value changed over time. And this corresponds to how many policies, you know, exist in the list of generations. So you can't just track to see, oh, this is converging or not because the metagame value is increasing or decreasing, right? This is not going to be a monotonic process. It's going to go, there's no rule about, we don't know ahead of time in general what the metagame value is. So here, if it goes up, you could say, oh, it's converging to 1, but no, actually, the true metagame value is 0. Now, what I'm showing here is the metagame solution for each player on every generation of this running. So this is like a stacked bar chart. So you could think of these are just like probabilities from 0 to 1. So on generation 1, we know the way we initialize this, right, is that we have 1 and 2. These are the initial policies we've set up. So we have rock, right, and then paper is the initial thing. Then what's being shown in each of these, generation stacks is what is now the new metagame solution after the best response has been added. And here, maybe it's better to look at this first. This is showing on every step, on every generation, which best response policy is actually being added. So on step 1, we add scissors and paper. Now, because I'm allowing this to copy, so like on generation 2, the best response is the same, right? So we have just a redundant policy. We don't have to add anything new. But for consistency, I'm keeping track of all the generations, even if they're duplicates of previous ones. So here, rock, and then, paper, scissors. So basically, by the time we get to the end here, we have now added all 3 actions to each agent's list of policy generations. And at the end of the metagame, now, we can see that the metagame solution has this 1/3 probability for each action. And then in earlier steps here, it was like 2/3 rock, 1/3 scissors on this step. Rock and paper. And we can see for player 2, like so it started out with paper. Yeah. So it started out with paper. And then we added rock and then paper. And then actually, this action isn't added until generation 4. We can see that as soon as it's added, or this is actually 1, So then as soon as it's added, then it becomes incorporated, on the next generation. And then the metagame solution is complete after this point. I'm sort of, I'm plotting this from the output of this function. We can also see some more information here, like how the metagame was built up over time. So this is showing the metagame history, which is the equivalent thing here to this. Sorry, not to this, but to this table, right here, because it's a zero-sum game. Again, I'm only showing the one value for player 1 here. And I'm also showing this is getting bigger than just 3, right? Because I'm allowing like repeats of the generations. It's fine. Here we can see the generations, and we can actually just see in the list if any of them are duplicates, right? So we have 1, 2, 3, 2. So here we have 1, 3, 3, 2, 2, 3. So there's some copies here, which just means that there's some redundancy in this matrix. Like some of the rows and columns are going to have identical values. So we can see these are the generations that were accumulated over time. And then this is the metagame we built up over time. Because it's this deterministic game, we have the only values in the metagame are -1, 1, and 0. Because, right, whenever we match up these policies, these deterministic policies, we are going to get either, win, lose, or draw outcome. And then each of these solutions, where we have a game value, probability vector for player 1, these are derived directly from each of these matrices. Where this matrix is just like a normal form game like we saw at the beginning of the book, this type of game, and this type of solution. So this is where, like, here I made this program here again where we can form just an arbitrary metagame like this. And then we can see down here what the minimax solution is. This is one with like 2 actions, but we can change these values and then see how the normal form game solution changes. But we have this program where we can in general solve minimax games like this, these matrix games, which is exactly what each of these in the history ends up being. And here's the best response history. Yeah. Okay, so sorry, I kind of went through a lot there, but are there any questions about applying this algorithm in this very basic setting? So in the book, they show how this progresses with this initial, actions or generation selection. Because we have this in this format, we can actually see how this solution evolves if we change the initial action selection. So for example, we could select action 1 for both players at the start and rerun this and see what happens. So here we see now it actually stops after fewer generations. And in this progression of the solution, the metagame value stays 0 the whole time. Right? So here we basically had scissors versus scissors, or sorry, paper. Yeah. Versus, yeah. So we had rock versus rock, then we add paper, right? Then paper versus paper. And then finally, so this is like a much more direct route to the solution, right? Where we more quickly here add all 3, and every round there was a draw in the game of these matchups. We can see what the metagame looks like here, right? Where on this step, we've already completed the full rock, paper, scissors game, right? Because we already have 1, 2, 3 in the generation list. So this is just a faster path to enumerating all of the actions. But we could see similarly, if we start with 1 and 3, we would get then an even longer progression here to the solution, right? Where now there's like more copied things. I mean, we still end up with the same solution. It just takes more. I guess it's the same number of generations actually as before, right? We probably will never end up with a situation where we need more than 6. Yeah. So whatever we do, we get basically 6 generations if the actions don't match. And then if we initialize it with the same action for both players, we get a much faster route to the minimax solution. Okay. Let me go. So yes, there's a note here. If we do this with so there are other cases here, like I didn't show it, but with the Prisoner's Dilemma game, that would be like a general sum game version of this. And this is a game where the Nash equilibrium is actually a deterministic one, right? Both players defect and that action. So here, like if we instantiate both with that action, then that will already be the Nash equilibrium. So that's one possibility, is that this generation 1 could already be at the Nash equilibrium. That's not going to be the case in a game like this, where the equilibrium is a stochastic one. But this is more an example of the key here is that the algorithm converged without enumerating all the policies, right? And this will be something that has to happen for this algorithm to be successful in general, right? Because we're going to apply it to more complicated problems. So actually, let me show an example of this. So we try to, now if we go to a more complicated case, now we're going to actually apply like a single agent algorithm to do the best response policy rather than just going through all of the actions. And we can actually see sort of a baby version of that here. I'm going to use this tic-tac-toe example. But this is exactly what I'm talking about when I mean like we fix the policy of the other agents. So here I have this game. This environment here is basically just a tic-tac-toe game. And I have a way of creating it where I'm fixing the policy of the other agent. Now here, this is a heuristic policy that we talked about a little last time when I made this this test environment. There are different heuristic policies that you can create. They're not at all based on, deep learning or any type of reinforcement learning. They're just, algorithms you can write down. The positional policy is just one where it favors moves around the center. It always takes wins. It always blocks opponents' wins. It's just, it's the strongest of these heuristic policies I had. And now we're going to say that we are playing as the O player against this policy. Okay. Now here I'm training it. I'm using these tabulars. So when we have a tabular problem, tic-tac-toe is small enough, we can enumerate the whole state space. We can basically turn it into a tabular problem. And then we can much more likely get an exact solution because we can have, a distinct value for every state. We can actually, whatever the optimal policy is, it may be one where it needs a distinct action selection in every state, and a tabular setup will allow us to achieve that. So what this is doing here is it's creating this MDP with this fixed opponent, and then it's training here. This is training actually policy gradient. Or no, sorry, yeah, no. So this is training it, yeah, with a policy gradient method. And it's tracking the performance over time. And we can see that it gets this performance for the O agent of like 0.05. Now, we know that for the minimax solution in this case, the best that the O player can do, actually for either player, is a draw, right? So actually, one thing we can verify to see how well our learning algorithm's going, when we do this single agent training against whatever the opponent policy is, depending on the game we have, we might know ahead of time, like, well, it's always possible for the O player to force a draw, right? So that means we know that when we're training this, we should always get a value of at least 0 in the performance. If we get a value less than 0, it means we know for sure we didn't converge to the optimal policy. And if it's greater than 0, it means that we know that the opponent is not the minimax solution, which in this case, it's not, because this is just a heuristic policy. But this step here of training, where we create this MDP and then perform here, it's just going through rounds of training here, that this is the step in the algorithm where we train the best response policy. It's equivalent to the step in the rock, paper, scissors game where, I just checked like actions 1 through 3 to see which one is best response. And then this is a tabular version of it. So this is doing it with a nonlinear test where I'm actually using like a feature vector, and I'm using a neural network with some number of parameters. And you can see that these hyperparameters are not optimized at all, and this neural network is probably too small. We can see here that this converged to this value, right? It's definitely not converge. We also know it's not close to the optimal solution because the value here should at least be 0, not negative. It did start out, with a much lower value. So it did learn something, but did not converge to the optimal solution. Here, this value, so this version of the training we can see did converge to the optimal solution, despite being not being a tabular version of the problem, right? It's like whenever you deal with an approximation function like this in the neural network training, and there should be a note of that in the book as well, you're not guaranteed to actually compute the best response policy, right? Because maybe your neural network isn't powerful enough to represent that policy, or the algorithm you ran just didn't have time to converge. Yeah, there's a note here, using RL to compute. So this is like, you can see like the way I've run this here, it took like 100 seconds to compute this best response. I'm also kind of running it very thoroughly to convergence. But again, this is like a way longer period of time than you would need in the simple other game where you just check the 3 actions, right? So this process could be extremely slow if you have to run this full RL learning algorithm on every one of those steps of the best response computation. But let me, okay, so this, let me show an example of this that I actually cut off after a certain number of generations. So here, I'm sort of now testing this on a different game, right? So now instead of just doing a simple like game like rock, paper, scissors, I'm now running this on still a very simple game, but one that has a lot more states. And that's this tic-tac-toe game. Okay. And here I'm actually, to test the correctness of the algorithm, I'm going to use these tabular features, right? This effectively converts the problem into one where I can more likely get an exact solution on every step. And we can see from these what the best response policies are, that it is in fact basically finding the true best response policy, or like one of them, right? There could be, in a game like tic-tac-toe, you know that there's a lot of equivalently good moves, also due to the symmetry of the game. So, there are many optimal policies in a game like tic-tac-toe. This training procedure will just produce, one of those in general. And then, yeah, so this is going to run with these hyperparameters, and we can see what happens here. So initially, I've seeded this with just the random policy, right? So both players have a random policy in the game. And this is the metagame value, which is also just the game outcome when the 2 random policies play each other, right? Tic-tac-toe, when both players play randomly, there is an advantage to the starting player. That's why this value is greater than 0. Now, what this is saying, see, finish training agent 1 best response. So what this is doing is on every step now. So the first step is it trains the best response policy to what is initially the random policy. And we can see the performance here is very high. It's not going to be 1 because we know that in tic-tac-toe, there's, even with random play, a random player could force a draw, right? If they randomly select the moves that force a draw, right? There's no way to guarantee a win in tic-tac-toe every time, even against a random player. And it's also worse for the O player, right? Slightly less of a chance of forcing a win because the X player goes first. So there's just fewer opportunities for the O player to win. And we can see that now, after training these 2 best responses, we can actually see the metagame history here. This is much longer now. So, and we can see what this metagame looks like in tic-tac-toe. So this is the initial matchup of the 2 random policies. Now we add, right? So this is showing our first best response performance against random, and then this one, right? So in this case, negative values mean it's good for the second player. This is what we would expect. And we could see that actually these 2 policies that we trained against the random one happen to play a draw against each other. Now, if we're lucky, these 2 policies that we trained will already be the minimax. Like, we know the minimax solution in this case is a forced draw, every time. And if you run this, I have seen when I've run this at times that the policy that is learned here on this step, or maybe on the first 2 steps or 3, already gets to the minimax solution. But that is not guaranteed to be the case. We can see here that now the training continued. So initially it's effectively a draw, this matchup. And then we train the best response again. And we see that, okay, so actually, here's an example. So here, we can actually see what went wrong here, which is that, first of all, this would not have been an equilibrium solution yet. And one of the reasons for that is that we can see that agent 1 on this round can actually achieve a performance of 1, which means it wins every time, right? So that means that the best response that we trained from the O player against the random policy, while it was a draw against the corresponding best response from the X player, this policy, if we then fix it and train an agent to exploit it, is one in which the X player can win every time, right? So clearly, like, this process would have to go on longer because this policy from O is not the minimax solution, right? It's not forcing a draw every time. Now, I can see already the way this ran that actually there's a problem here, which is that we did not converge to the best response, right? And I know this isn't the best response, although it's very close to it. The likelihood is the best response here has a performance of 0, right? Now you can see it's very easy for this to have learned something just slightly worse than the best response policy, right? This performance is just a little bit below 0, but it still creates a messy metagame now. Because really, this metagame should have really clean fractions, just the way this game works. It's simple enough that the metagame should always look like that. And here we can see that because this policy is not actually the best response, now we have a weird looking metagame where we have a metagame value here, and then we have a mixture of the random policy, and then this is like 37% of this policy that was trained that's not optimal. And we can see now as we go on, now we're skipping over now, like, it makes sense that the metagame solution should zero out some of the policies over time here. Right after 3 generations, we have this 1/3. This means that when the policies are selected according to these generations, there's a 1/3, X wins 1/3 of the time. And we would hope that over time, as we keep training these best responses, that we can see we get a lot of 1s here. So agent 1 is frequently finding a solution it can win 100% of the time. We would hope we would eventually converge to the minimax solution. But if you look at a game like tic-tac-toe, you know that if we're actually enumerating all of these policies, there are a lot of deterministic policies that exist in tic-tac-toe, right? We could try to come up with, like, an upper bound on it or a lower bound on it. But, it's many thousands, maybe hundreds of thousands of distinct policies that we could have. And if this policy response oracle algorithm gets stuck in a weird metagame where it keeps training best responses, but they're not optimal, or we get weird metagame values, we end up with a situation where even after 10 generations, we have a metagame that looks like this, but we're not necessarily closer to getting to the equilibrium solution, right? And that's the thing that can happen with this. And I'm not sure, there's a lot of stuff I still don't understand about how to get successful convergence of this algorithm, whether you should use value function training or not, but it seems like it is very susceptible to getting stuck. And of course, this is a game where I know the exact solution, and anything like this would be very unsatisfactory because we know, like, this is not the optimal solution. When this has been tested in other papers, like, let me show actually an example here. So this algorithm is based on, it's mostly based on the work from this paper. And this paper is basically doing the same kind of best response training, And there's a lot of good theory here from just traditional reinforcement learning explaining how this works and how it is guaranteed to converge. And one of the reasons it's guaranteed to converge is that there's this finite number of stationary deterministic policies for a given MDP. The problem is, of course, we don't want to have to go through all of them, because even though it will converge, it might take forever, right? So there's a description here of this double oracle algorithm. And it's basically the same algorithm that we're looking at, except that they're only looking at it in the tabular context, where they're training the best response policy. They're looking at this in a robot setting where there's sort of a grid and there's a fixed number of actions. And they are looking here at the grid size and how big, and how long this is taking. So when this paper came out, they were only looking at these sort of tabular solution methods where you can have a lot more guarantees on the convergence, as opposed to what was done later. What's in the book really, this later paper shows, this is sort of a summary of the oracle algorithm from that other paper, where we compute the best response, right? And then we have new strategies, and we keep this restricted game here. This is like called the metagame in the book. And then we just do this until like the metagame can't find, there's no different best response to the metagame solution. And this paper is more introducing this algorithm in the context of it's basically the same algorithm. It's just that instead of looking at it in the context of these finite number of stationary deterministic policies, we're looking at doing more like policy gradient training in a problem with like deep neural networks, where we're representing the best response imperfectly as a policy function, but essentially doing the same algorithm. It creates more, like you could see here, even in the tabular setting I did here, where this should work, you have issues here like where this didn't completely converge and it can screw up the metagame. In the policy gradient setting, that problem could be worse, because like we're probably never going to converge to the exact solution. But on the other hand, we're probably using that in the context of problems that are much more difficult to solve, where maybe this is the best we can do, and maybe the metagame evolves in a better way, because, I don't know, if you have small games like this, maybe it's easier for the metagame to get stuck. But if we look, so this is this original paper. They did these experimental results. Yeah, and they're talking about how like, so they had to limit the problem size here. This is sort of the pathfinding thing they're talking about. So they intentionally limited the problem size here to something where the, they could solve it in this finite number of time. They didn't, these aren't like, these grids are not that large. This is definitely tractable for a computer to handle. And then there's this important note here where if the algorithm ends up considering all the rows and columns of M, where M, this is related to the, the sort of policy space of the game, it will be slower than just solving the game directly. However, it is reasonable to expect in practice, many pure strategies will never enter the rows and columns. So this is what, it is reasonable to expect in practice. I mean, obviously there's no guarantee of that. We can see. And here, even in this simple example, we can see if you set up the problem wrong, or there's maybe hyperparameters and things that should be changed about this. Part of it is also the seed values. How does the seed work? There's different ways of constructing the random policies. You may end up with a metagame that just keeps evolving and takes forever. So this is sort of like introduction to this algorithm. We only looked at the zero-sum game minimax setting. I think we'll stop here for now, and next time we'll look at, hopefully I'll have a better sense of how this works in different contexts, and we can show look a little more at these meta strategy solvers, where we can actually go back to some of these algorithms, again, from the first half of the book, where we looked at joint action learning. You can see an example of it here, where we had algorithms like this. This is an example of this this is a tabular algorithm in multi-agent reinforcement learning that is designed to find equilibrium solutions. And here, this is applying it to the rock, paper, scissors game. But this algorithm can be used to find the we can actually apply this to the metagame, right? We can turn the metagame into something we can use this algorithm for. And then we can go back and use all these tabular solution methods we had developed on the metagame to then extend this policy response oracle to general sum games, right? Because in the zero sum game case, we know we have the solution. We can use the linear program to calculate the game solution. We can't do that in the general sum case, but we can use one of these meta solvers, we would call them, or more iterative algorithms to solve the metagame. And if the metagame is just a matrix like this process doesn't take very long to compute this. It's not exact. We introduce more inexact solutions, but hopefully next time we can look at this in more different problems than just simple rock, paper, scissors, and see maybe the criteria under which it converges easily or it gets stuck. So I don't know. Any questions about we talked about so far for this section? I mean, we basically did, at least in terms of the theory side, we did cover all of this part of the chapter. The only thing left in the book actually is this discussion of alpha star, which is an extension of population training.